All right, this is Mr. McCord's AP Chemistry class. We're continuing on with equilibrium and getting into some of the final touches to make everything come together. Okay? Namely, we're going to focus on something called Le Chatelier's principle, which tells us how things are going to operate when an equilibrium is messed with. When we scramble something, when we change the amount of a reactant or a product, or we change the temperature that they are at, or we change the pressure or volume of a container, and so on and so forth. So part of chemistry is not just looking at how something rests at equilibrium, but how we can, for one thing, shift something towards an equilibrium, and also how we can change an equilibrium to favor what we need, whether it's the reactants or the products. Okay, the example I have up here is a classic. This is a reversible reaction between N2O4 and two particles of NO2, two molecules. All right, or we could scale it up to a mole or more. So for every mole of N2O4 that breaks down into 2 moles of NO2, we also have 2 moles of NO2 that form back together into one N2O4. So at equilibrium, this process of the forward reaction, the N2O4 breaking into 2 of these is same as the rate of the reaction of 2 of these coming back together and forming one of these N2O4s. So no net change happens. Maybe some particles meet and some of them don't, but in the end, in the big view of things, the concentration doesn't change and the pressure doesn't change. Okay, but let's say we're not at equilibrium. Okay, before this, I've brought up the reaction quotient. That's this Q for quotient. Okay, but we haven't really used it a whole lot or talked about what it's useful for. So, say I have this reaction going. I load in some N2O4, that's this dark brown gas. I put it into a container that I can control. I seal it in, right, so that the gas can't escape. Right, and I let it settle. So I start with just N2O4, just this brown gas, and surely enough, it's going to start this reaction moving to make some NO2, all right? And the reverse reaction will also happen. But before I let it totally settle out and reach equilibrium, I can still calculate the ratio of our products to reactants with the coefficients of the reaction out as exponents, like this 2 here comes an exponent here, the 1 comes an exponent down here on bottom. Okay, so let's say I punch the numbers in, okay? And before I hit equilibrium, I get a number like 0.13, okay? Q, like K, is unitless, so there's no units to tag on here. So I've got a number that is less than what my equilibrium constant typically would be at this temperature. In this case, this is data for 100 degrees Celsius. Okay, so that puts me about right there. Well, what does that tell me about the reaction that's happening? Since this is a ratio of products to reactants, okay, and it will eventually reach equilibrium here, it will become this number, okay? Well, since this number is smaller, it's going to have to become bigger and bigger and bigger, up to 0.14, 0.15, 0.18, until I finally reach 0.212, okay? Well, what does that mean? What does it mean for the Q to start getting bigger and bigger and bigger? Well, the stuff on top is going to continue to increase, and the stuff on bottom is going to continue to decrease. Okay, makes sense. I get a bigger number here if this stuff is bigger and this stuff is smaller. Fine. Okay, these are my products. My products are increasing. My reactants are decreasing. Okay, well, is that coming from the forward reaction or the reverse reaction? If I'm making product and consuming reactants to do it, I'm moving the reaction more in the forward direction, or we say we're shifting the reaction in the forward direction. Okay? You might also say it's shifted to the right of the equilibrium. just kind of reading the reaction left to right. All right. So at this moment in this snapshot, my reaction is shifted to the right, okay, of this. It's shifted in the forward direction to produce more of this NO2 and to use up some of this N2O4. Okay, so my reactant's going down and my product is going up. Okay? So we can learn something about the state of the reaction before it reaches equilibrium. Now, does that mean that the reaction is only going forward until it reaches equilibrium? No, not even close. It's still going to be moving back the other way. Okay, but the rate of the reaction forward is going to be dominating over the rate of the reaction in the reverse direction. Okay, so when we say shifted to the right, that doesn't mean that the reverse just shuts down. Okay, it means that they're both going at the same time, but our forward reaction is kind of superseding the reverse reaction. And as a result, more of this kind of happens until we reach equilibrium. Well, let's say I restart this reaction and I just pump in a new set of particles, shake the container up, maybe I change the pressure or the size, the volume of the container a little bit, and then I take more measurements. Okay, before we reach equilibrium, I see what's going to happen. My new Q value, my new reaction quotient, comes out to be 0.78. That puts me at a larger number than my equilibrium constant. Okay, well, if I want to reach equilibrium, as the reactions continue to change rates until they reach that point, until the rate of the forward reaction is the same as the reverse, which one's going to be kind of winning out? Well, in this case, I need to get a smaller number for my Q until I reach 0.212 when I reach equilibrium. So that means that this number up on top, my product, needs to get smaller. It needs to start decreasing. And I need to use some of this up to push this over and make some more of the reactants. Okay? That is indicative of the reverse reaction, going from the right to the left. Okay? So this would be shifting the reaction left or towards the reactants. Okay. So, in short, we can make a relationship between the Q and the K. If our Q value is greater than our K value, okay, that means we are going to shift in the left direction. We're going to shift back towards the reactants. And if our Q is less than our K, we are shifting to the right to generate more products and use up some of our reactants. Now, these two kind of little things are sometimes a little bit hard to keep track of because it's like, oh, is it less than, greater than, left, right? So I always like to draw out a number line like this. Okay, it's way easier to doodle this out than to just try and memorize. Okay, if Q is less than K or greater, or K is less than, we can look at it like this, okay? Whichever way you have to move on the number line to change to that K value, to go from your value of Q to K, that's the direction of the reaction that is pushing harder, okay? That is predominating, that is at a faster rate, that is shifting, okay? Quote unquote, okay? Both reactions still happen, but we've got something kind of winning out, okay? Same thing goes for the reverse. If our Q is bigger than our K, we've got to shift back to the left, just like we would move on the number line to reach our K value. Okay? I think that's way easier to keep track of. Now, also, you can think of it as the Q setup, because this will always be there for you. Okay? Think of how your products and reactants are arranged. Products on top, reactants on bottom, and what that means for the value that pops out. Okay? So, less than, greater than, less than, greater than. When Q equals K, that is at equilibrium, so we land right smack dab on top of that value. Okay, so the reaction quotient can tell us a little bit about which direction the reaction is going to push harder on until we reach equilibrium. Okay, that can be helpful for having a strange set of initial conditions that don't put us at equilibrium, or it could even be useful for situations where we mess up the equilibrium. Like maybe I'm going to add in more reactants, or I'm going to release some of the products. I'm going to siphon it out. Okay, or maybe I change the pressure of my container. Okay, so this is going to lead us into how we use this concept of Le Chatelier's principle. When we mess with an equilibrium, what is going to happen? Which way is this going to shift? How is our Q going to show up? What does that mean about reaching back to the equilibrium, that K value? Okay? And how do we use that to push a reaction in the direction that we want for maximum efficacy? Okay. Let's apply Le Chatelier's principle to this reaction. Okay, we've got a new equilibrium where we are just kind of straight up following the reaction equation just so it's a little bit easier to keep track of. So this is at equilibrium right now. But let's say I mess this up. I purposefully pump in more N2O4. So let's do that. Okay. So we now have more N2O4 over here, which means our equilibrium is disturbed. It is different now. So we should look at the Q value. Okay? If I have now increased the amount of N2O4, my reactant, over here on the left side, then let's see, which of these is going to change? Well, the bottom is going to get bigger. Right? I'm going to have a larger value down here, which means my value for my equilibrium constant is going to be now smaller. I'm going to get a smaller number for my Q compared to the K that I should be resting at. I should be somewhere over here. With a Q less than K, I'm going to shift my reaction to the right towards the products. Okay? I'm going to end up pushing this reaction over more in the forward direction to make more of my product, to get a bigger number up here, a smaller number down here, and to reach back to my original K. Okay? So the reverse direction will continue happening, but eventually the faster rate of the forward direction will keep moving stuff over to this side. And then one of these will move there, and then back, and then there, and then back. But this is the ratio that we're going to settle out with. Okay, still that kind of 1-to-2 ratio we had in the beginning. Okay, so Le Chatelier's principle predicts that when you increase the concentration of something, right, you are going to push the reaction direction that uses that extra stuff up. So if we increase the reactants, we're going to push the forward direction so that we can use up those reactants. Okay, so one way of looking at it is how your Q value is going to change, but I kind of like just looking at it like this. I say, if we've got extra stuff of this, I've got to use it to get back to where my equilibrium was. You can kind of think of it like a pile of sand on the beach, right near the shore. As the high tide comes in and sort of washes over it, it's going to push that hill of sand down flat. Okay, so if we've sort of piled up more N2O4 over here, naturally we're going to end up washing it over into the products. Okay, we're going to use it up. Okay, so let's think of it the opposite way. Maybe I go and remove some NO2. I just go in and I take some stuff out. So I now have way less of my product here. Okay, well, what does that mean for my Q? Okay, well, that would mean that my number up here would be smaller, and this would be bigger. So my number is going to be smaller. So I would still move in the forward direction. But that should make sense. Okay, my equilibrium was kind of, in this case, a 1-to-2 ratio. Okay, it's not always going to be like that, but I can look at my K to figure out what direction that's going. Okay, in this case, I still end up with a Q that's over here, which means I'm still pushing in that direction. And I still like the sort of beach sand example. You can think of it like this. Instead of having a hill, we have a divot. We've kind of dug a hole over here. All right. So as we push the sand around, it's going to end up filling up that hole. Just the same, if we end up with less product, we're going to work the reaction to fill in that gap of products to get us back to the equilibrium we had settled at. Okay? So we push our reaction around to kind of reset what we messed up, what we changed about the reaction when it was at equilibrium. Okay? So if we increase the concentration of a reactant, we're going to use it up. If we increase the concentration of a product, we're going to use it up and go in the reverse direction. So let's say, let me change colors. Let's do orange. So let's say I increase how much of my product is here. So if I want to fix this ratio here, now that I've got a bunch of product, I'm going to have to get that product to be used up. Right? I'm going to have to push my reaction to the left. Okay, to remake some of the reactants that I kind of now don't have, or to use up some of the product that I have extra now. Okay, and same thing would go with if I removed some N2O4 like I did over here. Okay, the net reaction direction that wins, the faster rate, is going to go back in the reverse direction, shifting towards the left. Okay, so I should see kind of a net change of my products turning back into the reactants to fill that gap or to use up the extra products that I have now. So reactants and products and forward and reverse is just kind of relative. Okay, we can push a reaction forward or reverse just depending on how we mess with what's in our reaction. Let's make this a little bit trickier. So maybe I'm not directly changing how much reactant or product I'm dealing with. Maybe instead I change the size of the container, or I change the pressure inside the container that things are going on. This really only works for gases. Okay, so we're going to focus on gases here. So looking now at a QP and a KP. Okay, we're not directly using volume in any of these calculations, but it does affect the pressure. Whenever we deal with gases, pressure and volume are inverse. They go opposite directions. That's Boyle's law. So, okay, if my volume is shrunk down to a smaller size, my particles are going to have a higher pressure because they're colliding with the inside of the container more often, more frequently. Okay? If my volume is increased, I have more room for my gas, then they hit the walls less frequently, so there's less pressure on the inside. Okay? So pressure and volume are going to go opposite directions. Okay? Now, the way that this is going to work out is comparing the number of particles of gas in the reactants versus the number of particles of gas in the products. Okay, so we're not going to worry about, oh, is N2O4 going to have like a heavier hitting, force behind it compared to NO2. We're going to treat all our gas particles basically the same. The main difference is how many gas particles do we have on the reactants versus how many do we have in the products. Just looking at my reaction equation, right, I have 1 mole of N2O4 for every 2 moles of NO2 that I get from this reaction happening, and vice versa. Okay, so if I'm going to change the pressure or the volume, I need to make sure that I either shift to the left or the right to fix that equilibrium, to reestablish it, to kind of make the same conditions by changing kind of which side of the reaction has more of this or more of that. Okay? I'm going to focus just on how many particles of gas there are to collide with the walls of the container. So let's say that I am going to shrink the volume of the container. I'm going to squish this into a smaller space. Okay? Well, that's going to increase the pressure on the gas as I squeeze them into a smaller space. Okay? Well, our equilibrium was back where they weren't so squished, so I want to unsquish them. Well, how do I unsquish them? I have less particles. Okay? Now, don't get me wrong, the mass inside here is not going to change. I'm not going to destroy a particle, completely annihilate it, or I'm not going to let them escape. But if I can take two of these particles here and combine them into one of these, that's going to take up a little bit less room, and it's going to have less pressure because I have less particles banging on the inside walls of the container. So, to fix the equilibrium, I've got to make less moles of gas, okay? All the same mass is there, but I've condensed them into less particles, okay? I now have more stuff bonded together, okay? So, my pressure is going to kind of get relieved as I put some particles back together so they're not taking up so much space. They're not so squished and pressurized inside the container. Okay? Let's try it the other way. Maybe my volume is increased. Okay, well, I now have more room. That also has messed up the equilibrium. Maybe you wouldn't think of it as much of a stressful situation. We're not pressurizing it, we're giving it room to breathe. But that's still not equilibrium for this reaction, okay? It needs to fill that space. It needs to have more pressure, okay? So to get more pressure back, we need more particles of gas. So we're going to push the direction of the reaction forward to the right, okay? Now, we can also look at it in terms of changing the pressure instead of just always changing the volume, but the ideas are the same, okay? Remember that to reestablish equilibrium, we have to kind of fix whatever we've broken, in a sense, okay? And we do that by looking at whether the forward direction of the reaction or the reverse direction of the reaction does that for us. And again, for pressure stuff and for volume stuff, for equilibrium and Le Chatelier's principle, we're always just going to look at how many moles of gas we have total on the reactant side versus the product side, instead of trying to figure it out in our heads, like, oh, what's the pressure? If we can calculate a Q, with actual pressure values, that's great, okay? But try not to strain yourself too much on a problem that might be as simple as which side has more gas particles, okay? And I reiterate, total. If you have multiple reactants or multiple products, we're adding up gas particles together in the reactants and totaling up in the products like they're all the same kind of gas. We're treating all gas particles the same. We're using the rules of the kinetic molecular theory. There just isn't a big enough difference from one gas particle to another for it to make a huge difference for our purposes here. So a gas particle is a gas particle. No matter how big or small, what element it's made of, we're just treating it all the same. Now, as a disclaimer, what I'm showing with the particles is kind of a simplification of what's going on here, because this is going to be on a lot more massive scale. The forward and the reverse reactions are happening constantly in both directions. And also, this ratio doesn't really hold up the same way as it does in the equilibrium constant, since this is squared. So, if this was truly my, ratio of, 2 to 4 over here, it wouldn't be like a ratio of 2 to 4 truly. It would be 2 on bottom, 4 on top, squared. 4 squared is going to be like 16. So, the way I'm showing this is not, exactly technical. So, don't, take it for fact or something like that. It's just to get you to see it, okay? Here's kind of a tricky one that always kind of frustrates me. It's kind of like mental gymnastics. What happens if we change the temperature that a reaction happens at? Well, in order to predict how the equilibrium shifts around, we need to know a little bit more about the reaction. We need to know whether it is endothermic or exothermic. Okay? So in this case, our reaction here, our reversible reaction, has a delta H value written in this direction, okay, that is less than 0. In other words, it is negative. In other words, it is exothermic, okay? So heat is released as this reaction moves forward. But what does that say for how it affects the equilibrium when temperature changes? Well, let's just say we increase the temperature. We're just going to get this thing hotter. Things are going to start moving faster, and then see what happens. So temperature is going up. Okay. Now, before, when I mess with the reaction, I want to kind of fix what I've messed up. I want to either use up extra reactants or fill in a gap of reactants or products. I want to fill the space or kind of shrink the amount of particles of the gas I have to fit the size and pressure of the container. In this case, temperature is just kind of affecting how the reaction goes energetically. But I can also look at it as, where am I using heat and where am I giving off heat as a product? Okay? If this is an exothermic reaction and heat is being released when it's written this way, okay, that means that heat is going to be like a product. So let's just write it like a product. Sure, it's not a chemical, but it's going to be released as it's put out here. So we're going to treat it like the other stuff. Plus some amount of heat. Now, I don't know exactly how much, but whenever this reaction moves in the forward direction, then I'm going that way. Now, if we think about it, this is like saying I'm producing heat like a product, okay? And my equilibrium is going to shift and either make heat or use heat to kind of get everything back to normal. Okay? So if my temperature is going up, you could say that everything's getting hotter. You could say that everything has more heat to use. Okay? So if I want to use up that extra heat, I've got to use the direction of the reaction that uses up the heat I would otherwise make. If I push this in the forward direction, okay, I would make more and more and more heat in a situation that's already getting hotter. Okay? And that would just perpetuate itself. I need to undo this, okay? So I need to start using up some of that extra heat that has come about from the temperature raising, okay? So I'm going to end up shifting to the left, more in the reverse direction to use up the heat. Okay? Now, we can also look at that for an endothermic reaction. If heat was over on this side and my temperature is going up, I will want to use up the extra heat there by pushing the reaction this way. Okay? So this one's a little tricky because it depends on whether your reaction is releasing heat exothermically, like this one, or if it is using it up as a reactant, okay, over here. So if my endothermic reaction has temperature increased, then I would push the reaction forward to the right to use that heat, okay, to make my products. All right? It all depends on the situation and what reaction you're using and what enthalpy change value it has. Okay? Well, what happens if I cool it down? So if I'm cooling this down instead, then my situation, my system essentially has less heat, if you want to think of it like that. So to make up that gap, that loss of heat, I've got to churn some more out. Okay? Well, my heat is in my products. So I want to make more products to make more heat to offset the fact that I've lost some from the temperature lowering. Okay? So I'm going to push this in the forward direction. Okay? If my temperature's going down, I got to make that heat back up. I've got to start releasing it by pushing the reaction in that direction. Okay? This is yet another way we can control how a reaction moves forward or reverse based on something we change about the reaction system. Okay? Now, something that is different for temperature is we're not really changing the value of Q here because our concentration isn't changing, and maybe you can make an argument for the pressure and stuff, but really what we're doing is getting a different K value. After all the K values we've looked at so far, usually have some little note. It's like, oh, this is at 100 degrees Celsius, 25 degrees Celsius, 500 degrees Celsius. It's always got to say it's at a very specific temperature, okay? If I'm changing the energy that the reaction is taking place at, that average kinetic energy, that changes how easily reactants can change the products or vice versa, okay? More energy means more, possibilities, easier to break bonds and reform them and all kinds of stuff. So I can't treat it like it's the same equilibrium. So this one you can't really think of in terms of Q as well, because I'm not shifting the Q and see how we move back to the same K. I'm changing where the K is, and then I'm having the reaction kind of reach that new K. Okay? So yeah, maybe your pressure does change a little bit. Maybe you do get a different Q value, but your K value is also going to change. So these kind of problems with temperature, I like to think of kind of in this way. How am I going to move it around without thinking about Q, just by either replacing lost heat or by using up extra heat, okay? Whether your temperature is lower or higher for an exothermic reaction. It's reversed for an endothermic reaction. But again, just as soon as you know whether it's exothermic or endothermic, write down your heat as a product or as a reactant and see how you feel the need to fix the equilibrium. Now, as we've seen here, just plugging in concentrations or partial pressures into a Q or a K is not the only way to look at how an equilibrium is, what the state of it is, whether it's in equilibrium or it's shifting back to equilibrium, things like that. Okay? There are observable properties for solutions and gases that we can use to also see how something is returning to equilibrium. So this is a personal favorite as well as a favorite among many teachers and professors, because we can visually see the change between our reactants and products by their color. Okay? Essentially, the darker this cloud of gas is, the more of this N2O4 we have. The lighter it is, the more NO2 we have. And you can see that shift in real time as you change the pressure or the temperature that the reaction is under. Okay? In other situations, you might measure differences in pH. Or if you are pushing around the reaction, if it's endothermic or exothermic, you might measure a temperature change. Okay? So equilibrium can get pretty complicated, but there are simple ways for us to figure out what is happening down there, how the rates of the reactions are changing, what is predominating, which way we are shifting the reaction. Okay? So don't get too caught up in the kind of specific stuff. Try and think of it as, what is the equilibrium like? How do we fix it? How do we return to that place? How do we undo what we have messed up? And how does the reaction do it for us?